Namaste and a very good morning to all of you. I welcome you to my channel, The Outlier. My name is Mithun. In today's video, I'll be talking about a very interesting technique called as PCA or Principal Component Analysis. Even before I proceed to demonstrate how to work with PCA using SPSS, may I request you to subscribe to my channel, also like and share my videos. Let me begin by asking a simple question. What exactly is PCA? Where do we use PCA? What are the advantages and disadvantages of PCA? If you are new to the world of statistics, these terminologies might be terrifying. So I'll make an effort to break this down in the next few moments. What exactly does PCA stand for? PCA stands for Principal Component Analysis. I repeat, PCA stands for Principal Component Analysis. PCA is a technique which is used to simplify complex data by reducing the number of features while keeping most of the important information. PCA is an unsupervised machine learning technique, which means in the case of PCA, we do not need a dependent variable. It is particularly suited when you have a high dimensional data. The word dimensions refers to variables or columns. Imagine that your manager gives you a data set with 60 or 70 columns. It becomes very difficult to process 60 or 70 columns. So what we typically do is reduce the 60 or 70 columns into 4 or 5 manageable subset of variables. How do we do this? The process of reducing from 60 to 4 or 5 important dimensions is what we can call as PCA or Principal Component Analysis. What are some of the important advantages of PCA? There are 4 main advantages of PCA. The first is it reduces complexity. It makes data easier to analyze by reducing the number of variables. Number 2, it removes noise from the data. That is, it filters out irrelevant information. Number 3, it improves visualization. PCA helps in plotting and visualizing high dimensional data. Number 4, it speeds up computation. PCA helps us expedite the process of computation. Less data to process means faster analysis. As with any technique, PCA has its share of disadvantages. I'd like to highlight 2 important disadvantages while working with PCA. First, loss of information. When we work with PCA, some details may be lost in the process. Number 2, interpretation challenges. The new features, which we are going to call as principal components, can be hard to understand. Let's now proceed to look at 3 important application areas of PCA. PCA has a lot of advantages in data compression. One of the main application areas for PCA is in the field of data compression because it reduces the size of the data for storage. The second area of application is image processing. PCA simplifies the image data for easier analysis. Number 3, pattern recognition. PCA identifies patterns in large datasets. With this background about the PCA technique, let me now proceed to show you the data set that I'll be working on. As you can see, this data set is called as wholesale price index data. I have extracted this data from Ministry of Commerce website. I have got approximately 10 years of data starting from January 2001 all the way up to April 2010. What are some of the important columns in this data set? As you can see here, I have case number, date. I've got the wholesale price index of all the commodities. Next, I've got the wholesale price index of primary article, food article, food grains, cereals, rice. There are other important commodities here like wheat, jowar, then we have maize, ragi. Similarly, you have the consolidated wholesale price index of pulses. Then you have the individual breakup for gram, arhar, moong, masoor, urad. Similarly, there are a lot of other variables related to fruits and vegetables. You can see here, this is the wholesale price index of fruits and vegetables. We have the wholesale price index of vegetables like potatoes, sweet potatoes, onions, tapioca, so on and so forth. I have approximately 55 columns in this particular data set. Though I have non-food related wholesale price index information as well, I will be ignoring the non-food items and I will be mostly focusing on the wholesale price index of only the food items. What is the sample size in this data set? As you can see, I have around 112 records in this data set. As you can clearly see here, I've got 50 to 60 different columns, implying that this is a high dimensional data set. How are we going to work with such a high dimensional data set? Let me break this down in 10 steps. Let me now proceed to show you how we can perform PCA using IBM SPSS. As you can see here, this is the data set. I'm calling this as transposed data set. You're already familiar with some of these columns like case num, case label, wholesale price index of all commodities, primary articles, so on and so forth. Now, to perform PCA, what you need to do is in SPSS, you need to click on the Analyze menu bar. Remember, PCA is a dimension reduction technique. So let me choose the option dimension reduction. SPSS displays 3 options which helps me reduce the dimension. The first one being factor. So let me go ahead and select the option factor. As you can see, this opens up a new dialog box which is called as the factor analysis dialog box. In the canvas on the left hand side, you have all the columns. I have dropped out some of the irrelevant variables. In the canvas to the right hand side, you can look at the variables that I will be using for analysis like rice, wheat, jowar, bajra, so on and so forth. I've taken 55 columns here. It ends with tea and coffee. Now, what is the relationship among all of these variables? We will soon find out when we study the output of factor analysis. I need to make certain selections in the factor analysis option. One of the first things that I do is click on the descriptive statistics option. Let me go ahead and select the descriptive statistics box. You can see here under the descriptive statistics section, there are a lot of options. I'm mostly interested in 2 options. The first one is under correlation metrics, you can select coefficients. Why? This will produce a correlation matrix of 55 variables. The next most important option is KMO and Bartlett's test of sphericity. I'd like to highlight the importance of performing KMO and Bartlett's test of sphericity. Most researchers overlook this particular option. This is one of the most important options because this tells you whether the data set is appropriate for us to perform factor analysis. Unless you perform the KMO and Bartlett's test of sphericity, it is advisable that you do not use factor analysis. Once you have made these selections, you can go ahead and click on the continue option. The next option that you see is called as the extraction method. Let me go ahead and select the extraction method. This shows you a lot of options under extraction. Under the method of extraction, the default option that SPSS provides is what is called as principal components. Let me click on the drop-down menu. You have several other options like unweighted least squares, generalized least squares, maximum likelihood, principal axis factoring, alpha factoring, and image factoring. I'm going to go ahead and select principal components. Under the analyze section, you can go ahead and either look at the correlation matrix or the covariance matrix. Display. What do you want SPSS to display? I will go ahead and select the Scree plot. This is very, very important because a Scree plot tells us how many components should I extract. We have 55 variables. From 55, do you want to reduce it to 5 components, 4, 6? What is that optimal number? The best and the easiest way is through a Scree plot. The conventional method of answering how do you extract the optimal number of components is through what we call as the K1 criteria. K stands for Kaiser and 1 implies that the eigenvalue must be greater than 1. You can see here, we are specifying the extraction method based on eigenvalue. We are saying to SPSS, if the eigenvalue is greater than 1, you go ahead and extract the component. If not, ignore it. So that's a way or criteria of extraction of the components. Maximum iterations for convergence is 100. You can feel free to come here and specify a bigger number in case the algorithm does not converge to the optimal solution. I will leave it at the default number of 100 in this video. Let me go ahead and hit the continue button. The third option is rotation. Rotation of the components helps us interpret the components better. An unrotated component solution might be useful, but it might be extremely hard to interpret and comprehend. Therefore, what I'm going to do is I'm going to rotate the components. Let me click on the rotation method. SPSS provides 5 different methods. The first is Varimax, which is a very, very popular method. The second one is what is called as direct oblivion. Then you have other options like Quantimax, Ecomax, and Promax. The default option is none. I'm going to choose the option Varimax, which is a very, very easy, simple, and a popular method to interpret and understand the relationship between the original variables and the extracted components. If you want to choose the loading plot, you can go ahead and select the loading plot. Let me now hit the continue button. Next, we have what is called as scores. Let me go ahead and select the scores option. I have selected save as variables. What does this do? What this does is it creates new columns in the data set. I repeat, it creates new columns in the data set. These new columns can be used for advanced analysis for future iterations of our future projects. Let me now click on continue. The last thing that we need to do is options. You can see here, there's an options tab. Let me go ahead and hit the options button. These are optional things. You don't need to specify this for every data set. However, I am doing this for this video. Under the coefficient display format, I'm going to select sorted by size. What this does is all the variables which have a high loading for component 1 will appear right at the top, and those variables which have a low value for loading will go down. The next is suppress small coefficients. If a variable has a very, very low value of coefficient, I don't want to see it, and therefore I'm telling SPSS that if a particular value has a loading of less than 0.10, you can go ahead and suppress it. 0.10 is just, it is not a scientific number. It is not a sacrosanct number. You can go ahead and specify any number instead of 0.10. With these selections, let me go ahead and hit the continue button. So we have spent some time in asking SPSS to produce the output that we want. With these selections, you're all set to run the PCA method in SPSS. Let me go ahead and hit the OK button. What you're seeing here is the output window. SPSS produces a lot of output. As you can see here, SPSS generates the correlation matrix. What you're seeing here is the correlation matrix. You have a small table for KMO and Bartlett tests, communalities, total variances explained, Scree plot. Then you have the component matrix. You have the rotated component matrix here, component transformation matrix, and you have the loading plot. It is a bit difficult to explain each of these tables from the SPSS output window. So what I'm going to do is I'm going to explain each of these tables from the Excel spreadsheet. It's a lot easier to interpret and make sense of these numbers from Excel. I've copied and pasted all of these tables in SPSS. So let me go back to Excel. So this is the raw data which I showed you in the beginning of the video. Let me now proceed to show you the most important step in factor analysis. You can see here, I've named it as step 1, KMO and Bartlett's test of sphericity. Let me go ahead and select this. So this is the output of KMO and Bartlett's test. This is the prerequisite for you to perform PCA or principal component analysis method. There are 3 important conditions. The first is you need to have a minimum of 10 variables when you are performing PCA. If you have 6 variables or 7 variables, there is no point in performing PCA. The second one is we need to check the sampling adequacy. This is where a test called as Kaiser-Meyer-Olkin measure of sampling adequacy comes into picture. It's called as Kaiser-Meyer-Olkin. These were the names of 3 important statisticians, Kaiser, Meyer, and Olkin. They proposed a method or a formula to check whether there is sampling adequacy or not. The simple thumb rule here is if the KMO value is bigger than 0.7, it means that the sampling adequacy test is satisfied. On the other hand, if the KMO value is lesser than 0.7, it means that your data fails the sampling adequacy test. As you can see, the KMO value that I have obtained is 0.899, which is clearly greater than the threshold of 0.7. And hence, the data passes the KMO measure of sampling adequacy. The next criteria that I would like to look at is what is called as Bartlett's test of sphericity. If you are a layman, what is this Bartlett's test of sphericity? It is verifying whether there is sufficient correlation in the data for us to perform PCA. If there is no sufficient correlation, if you do not have sufficient correlation in the data set, it is advisable that you do not perform PCA. PCA is not the right technique for your data set. The Bartlett's test of sphericity reports the chi-square value as 16068. The degrees of freedom is 1540. However, I'd like to draw your attention to the significance value, which is 0.000. How do we interpret this number? 0.000 is less than 0.05. Since it is less than 0.05, I will reject my null hypothesis. The question is, what is the null hypothesis? In the Bartlett's test, the null hypothesis is that the correlation matrix is an identity matrix. The alternative under the Bartlett's test is that the correlation matrix is not an identity matrix. So since the p-value is less than 0.05, I can go ahead and confidently reject the null hypothesis and conclude that the correlation matrix is not an identity matrix. For those of you who do not want to get confused with this statistical mumbo jumbo, what you can do is you can pay attention to two numbers. Observe the KMO value. KMO value greater than 0.7 means that you have the license to do PCA. If the number is short of 0.7, PCA is not an appropriate test. It is better to stop right here. Second important number that you need to check is watch out for the p-value. If the p-value is bigger than 0.05, stop PCA. PCA is not the right technique for your data set. However, if the p-value here is smaller than 0.05, you again have the green signal. You have the license to do PCA. So these are two important prerequisites for performing the PCA. Now, we are through with step one, which is to watch out for KMO and Bartlett's test. What is the second step that we need to pay attention to? The second step is to watch out for the correlation matrix. As you can see here, this is the tab which tells me about the correlation matrix. You're already familiar with the variables: rice, wheat, jowar, bajra, maize, barley, ragi, gram, so on and so forth. These are the variables. For those of you who are very, very new to this, this is a correlation matrix. You can also call this as a heat map. There are three observations that you need to make. When you see dark green color cells, it indicates that there is strong positive correlation. When you see deep red color cells, it means that there is strong negative correlation. The third observation that you need to make is yellow colored cells, which indicate weak or negligible correlation. Ideally, if the data set is suitable for me to apply the PCA technique, I should be able to see a lot of dark green color cells or a lot of dark red color cells. Remember, correlation lies between -1 and +1. If these cells are exceeding 0.7, it means that there is strong positive correlation. If the cell value is less than -0.7, it means that there is strong negative correlation, which is a good sign. I'm very, very happy to note that there are a lot of cells which are green in color. I have highlighted this in red color border. You can see here, this is one set of variables starting with rise all the way up to urad. You can see there are a lot of green color cells indicating that there is adequate correlation. That is the first observation. Secondly, it also means that the wholesale price index of these variables are varying in one particular direction. And we should not be surprised if these variables come out to be under the first component. In other words, the correlation matrix gives us early warning signals about the output of the PCA. So wherever I've put a red box, you can expect this to be component 1. Let me scroll down. You can see here, there's another red box here, which means that this could be your component 2. Under component 2, you might find sapota, milk, eggs, marine fish, inland fish, mutton, beef, and buffalo meat, poultry, chicken. This could be your second component. These are some of the early warnings that I'm getting from the correlation matrix. I've put a third red color box here indicating that there are variables like pork, black pepper, chili, you have turmeric, cardamom, so on and so forth. All of these may belong to the third component. Let me scroll up and show you some of the other components that might come up. You see here, there's one more box for sapota, milk, eggs, so on and so forth. We have already seen this. There is a box that I've put for coriander, tea, and coffee. Roughly, when I examined the correlation matrix in greater detail, I was able to obtain 8 boxes. Now, this is indicative. This is not conclusive. You can see here, there's a box here. There is one more box here indicating that these are all variables which have the same direction of wholesale price index. So from the correlation matrix, there are 2 signs. One is that there is a healthy correlation between the variables. So PCA is again a good technique. And I come to the conclusion that possibly there may be 8 components in the dataset. If you want to be more sure whether 8 is the optimal number or not, we have to make a move on to step number 3. What is step number 3? We have to look at the eigenvalue. If you're very, very new to statistics, don't worry about these terminologies. Eigenvalue is simply the proportion of variance explained by each component. I've put a box here for a reason. As you can see here, this table is called as the total variance explained. The first column is component. The second component represents the eigenvalue for each component. The third component here is the percentage of variance, and column number E tells me the cumulative percentage of variance. How do we interpret this? Have a look at the first component and the eigenvalue. It is 30. It is clearly greater than 1. 30 is greater than 1. Second component has an eigenvalue of 5.7, again greater than 1. The third component has an eigenvalue of 3.6, again bigger than 1. When you have a look at the fourth, fifth, sixth, seventh, and eighth component, each of these 8 components has an eigenvalue bigger than 1, which means in our data, there are 8 components that are present. I'd like to draw your attention to the 9th component, which has an eigenvalue of 0.845. 0.845 is clearly less than 1. And therefore, we don't need to look at 9th, 10th, or 11th component. From the 9th component onwards, you can see the eigenvalue goes on reducing. We don't have to look at those components which have an eigenvalue smaller than 1. So this is one of the most important questions that a researcher needs to ask. How many components do I need to extract? This table conclusively answers this question. We have to extract 8 components. Why 8? I've just now explained. Eigenvalue greater than 1 is what you need to pay attention to. One other question here is about the percentage of variance. In the PCA, the first component explains the highest percentage of variance. Have a look at this. This is 55% approximately, which means that component 1 alone explains 55% of the variance. Component 2 explains the next highest percentage of variance, which is 10. Component 3 explains 6, and the subsequent components explain lesser and lesser percentage of variance. The third column here is the cumulative percentage. If you were to look at only the first 2 components, 54 plus 10 is 64, roughly around 65. If you were to look at the first 3, the cumulative percentage of variance would be 71. You may ask me how. 54 plus 10 is 64. 64 plus 6 is 70. And when you take into account the decimals, it will come up to 71. So the cumulative percentage of variance tells us what is the percentage of variance explained by the first 8 components. Hold your breath. It is 88%, which is not bad at all. Let's look at the total number of variables. We had 56. We can reduce from 56 variables only to 8 major components, which account for 88%. The remaining variables, that is 55 minus 8, which is 47, account for barely 11% of the variance, or should I say 12% of the variance. So this is the creamy layer of the variables which are accounting for a high percentage of variance. Again, if you're a non-statistician and if you're not able to make sense of the discussion, let me just give you a small analogy. If you are a cricket buff, if you watch a lot of cricket movies, let me just quote an example. Let us say there is a cricket match in which Indian cricket team has scored 300 runs in the first innings. And out of these 300 runs, Rohit Sharma has scored 120 and Virat Kohli has scored 150. Now, out of the 11 players, the total runs is 300, but only the top 2 players, that is Virat Kohli and Rohit Sharma, have scored 150 and 120 respectively. 150 and 120, if you add up, will give rise to 270, which means that out of the total of 300 runs scored, only the top 2 players account for more than 90% of the runs. That is, they account for 270 out of the 300 runs. That is, the giant share, the lion's share of the runs have been scored by 2 players. The remaining 9 players may have barely scored 1, 2, 3 or single digit, which we are not so concerned about. So since the dominant runs have been scored by these 2 players, they are our heroes. The same way, if you apply the same logic to the components here, out of the 55 variables that I had, not all the variables are important. Only the first 8 components, which account for 88% of the variance in the data, is important. That is the message that I get from the eigenvalue method. Is there an easier way of answering how many components do I need to extract? The answer is yes. Sometimes numbers can be confusing, so we can look at what is called as the Scree plot. Have a look at the Scree plot. The Scree plot shows you the distribution of the eigenvalue for each and every component. Along the y-axis, you can see we are plotting eigenvalue, and along the x-axis, we have the components. There are 55 components, And then we have the eigenvalue along the y-axis. What we need to do is we need to look at the eigenvalue greater than 1. You can see the red dotted line. We are interested in all those dots which cross the red color line. Have a look at the first component. It is exceeding 30. Second one is again exceeding my criteria. The third one is around 5. Fourth is around 4, so on and so forth. Approximately there are 8 dots which cross the line, again implying that there are 8 components in the data. This is the first component. Second component's eigenvalue. You have the third one, fourth, fifth, sixth, seventh, and 8th. The ninth one is actually less than 1. So this is what we call as the elbow of the graph. You can see here, this is what we call as the elbow of the graph. Some people, in fact, a lot of textbooks also call the Scree plot as the elbow graph or the elbow curve. In fact, this is the curve which is called as the elbow curve. You can see here, this is the curve which is called as the elbow curve, and this point where there is a dip in the value of the eigenvalue to less than 1, that is the point which we call as elbow point. Here in the ninth dot, the eigenvalue is less than 1, and therefore the dot corresponding to 9 in x-axis can be called as the elbow point. So this is what you need to remember. Watch out for the elbow. The elbow value of greater than 1 is what we are interested in. If it is less than 1, you can ignore it. If you're writing an exam, this is called as the elbow graph, and this entire line here, which is almost parallel to the y-axis, this line you can see is almost parallel to the y-axis. This is called as the elbow curve. And the point where the threshold of less than 1 is crossed, that is the point which we call as elbow point. Hope this makes sense. Let me now go to the next question. The next question is, what do these components represent? We have answered the first question. How many components? The answer is 8. Eigenvalue table and the Scree plot help me answer this question. The next question is, what do these components represent? Because the word component, factor are all very generic terms. Let's put some flesh and blood into that question. I'll now move on to step 5. Now, here you see what is called as rotated component matrix. I repeat, this is called as rotated component matrix. Here you can see the 8 important components. You can have a look at component 1, component 2, component 3, 4, all the way up to 8. Along the row, I have taken the original variables. We had rice, wheat, coffee, so on and so forth. As you can see here, I have put a label under each component. The numbers that you see here, 0.9, 0.95, so on and so forth, indicate what we call as the factor loading. In simple language, this can be treated as correlation value between the components and the original variables. When you look at the first component, this is the first component, it has a very high loading on coffee, wheat, pork, marine fish, maize, milk, jowar, dry chili, masoor, rice, so on and so forth. Why do I say high loading? Have a look at the values here. It has crossed 0.7. Some of them are 0.9, others have a value of 0.8. And as I scroll further down, you can see the values tend to reduce. I've taken approximately 0.6 as the cutoff. A lot of components are getting loaded into component 1. If you want to look at these variables and give a collective name, you can go ahead and call it as staple food and meat products. So this is our first component, which is explaining 54% of the variance in the data. That is staple food and meat products. Have a look at the second component, which is explaining 10% of the variance in the data. Now, corresponding to coffee, wheat, so on and so forth, you see blank cells. There are loadings, but the loading is very less, and therefore I have suppressed it. Otherwise, you have a lot of numbers and it can get confusing. Now, what are some of the variables that come under the second component? Under the second component, you can see these are some of the variables. You have items like grapes, green peas, cauliflower, tomatoes, mangoes, and apples. These are some of the variables which have a high loading on the second component. Since the second component mainly loads with fruits and vegetables, I have gone on to label the second component as fruits and vegetables. Let me scroll down. You can have a look at the other variables. You have the third component, which mainly comprises of inland fish, turmeric, and pineapple. Then you have the variables like poultry, chicken. You have cardamom, which is going with component number 4. Next, you have ginger, fresh ginger, and fresh coconut, which is loading with the next component. So on and so forth. Hence, for each, based on each of the variables, I've given a name to component 1, component 2, 3, 4, so on and so forth. For better interpretation of these components, let me go to step number 5. You can see here, this is the component name, staple food and meat product. All the items under staple food and meat products I have listed, from coffee, wheat, pork, all the way up to brinjal. These are the main items which go into component 1. Fruits and vegetables, just now you've seen the main variables that come here are grapes, green peas, cauliflower, tomatoes. You have mangoes and apples. The third component I'm calling as processed and specialty foods, inland fish, turmeric, and pineapple. The fourth component, you have variables like poultry, chicken, you have cardamom. This I've labeled as spices and condiments. The fifth one mainly comprises of root vegetables and tubers. There are variables like fresh ginger and fresh coconut. Variable number 6, rather component number 6, comprises of cabbage and potatoes, which I'm calling as leafy and cruciferous vegetables. Component number 7 comprises of garlic and other aromatics. Then you have lychee, which is component number 8. You can go ahead and call it as tropical fruits. So these are the 8 components. Remember, we have answered 2 very important questions. How many components should we extract? The second question is, what do these components imply? Let's now proceed to look at step number 7, which I'm calling as distribution analysis. All the components can be seen here, staple food and meat product. Then you have fruit and vegetables, so on and so forth. And the length of the bar indicates the percentage of variance. Clearly, you can see 54% of the variance in the data is accounted for by variables like component number 1, staple food and meat product. 10% of the variance is accounted for by fruits and vegetables. 6% is accounted for by processed and specialty food. As you look at some of the other items like tropical fruit, garlic, leafy, and cruciferous vegetables, their variance, the proportion of variance that they account for, is very tiny. Let's now proceed to look at step number 8. What you're seeing here is a path diagram. I have not constructed this path diagram using SPSS. I've used a separate software which is called as StatCraft to generate the path diagram. What you're seeing here to the left-hand side are all your original variables. The rectangles that you see on the right-hand side are all rotated components. The numbers that you see on top of the line represent the rotated, my apologies, they represent the factor loading. I repeat, these numbers 0.9, 0.9, they represent the factor loading. This is what we call as a path diagram. A path diagram gives you a visual representation of the relationship between the original variables and the rotated components along with the magnitude and the sign of the loading. We have discussed this earlier at the cost of repetition. Let me say this once again. Variables like pork, marine fish, wheat, dry chili, so on and so forth are loaded with component 1. Similarly, you have other variables like turmeric, inland fish, pineapple, so on and so forth, which are loaded with component number 4. Then you have certain other variables like grapes, cauliflower, tomato, and mangoes, which are loaded with rotated component 2, so on and so forth. So this is a very, very effective and a simple way in which you can summarize extremely complex information visually. Now that we are through with a path diagram, let us proceed to look at data post-processing. When we look at the correlation plot in step number 9, I'm showing you the correlation plot. Now there is a difference in this plot and the earlier correlation matrix that you saw. The earlier correlation matrix was created using original variables. This correlation plot is created using the rotated components. Along the diagonals, you can see 1 implying perfect positive relationship. The off-diagonal elements, that is the upper triangle as well as the lower triangle, has a value of 0. What does this mean? It means that each of our components are orthogonal to the other components, which means that the extracted components are independent of each other. That's why you're getting the correlation of 0. You can have a look at the color scale here. Blue color cells, if there is a high positive correlation, they are shown in dark blue. On the other hand, as you look below, you can see white color space, and white color space is indicated to show a relationship of 0. When you look at red color cells, they indicate negative correlation. Obviously, we do not have any negatively correlated components. Why is this important? Many times, you can use PCA as a standalone independent technique. Sometimes you can use PCA as part of another project, which means you can use PCA, extract the components, and use those new components as independent variables for regression. Remember, when you're talking about linear regression, one of the major assumptions of linear regression is that the independent variables are uncorrelated. If they are correlated, it leads to multicollinearity. The coefficients that you get in the coefficients table for linear regression will be unstable. The confidence interval will be wider. The predicted values will vary a lot and are untrustworthy. Therefore, you can look at PCA on the independent variables. You can use PCA on the independent variables, generate new components, and use these components as independent variables under linear regression. The advantage is that these independent variables are completely uncorrelated, and therefore they do not suffer from the problem of multicollinearity. The last step you can see here is step number 10. These are the original variables that we had, but when I scroll to the extreme right side, you can see here I have created the new variables. These are the 8 new columns that I've been able to generate. You don't have to use 55 columns. Henceforth, you can use only these 8 components for further analysis. So this is the beauty of PCA. PCA helps us reduce the data from a high dimensional arrangement to a low dimensional arrangement. How do you get these PCA scores in the data? Let me go back to SPSS. This is the data set. All that you need to do is scroll to the extreme right side. If you scroll to the extreme right side, you can see here SPSS creates the 8 columns. These are the 8 columns that SPSS creates, which you can use for further analysis. Now, I'd like to quickly summarize the learnings that we have got in today's video. This is the raw data. We were able to look at the raw data. The first step when you're doing PCA is to look at KMO and Bartlett test. Watch out for a KMO value of greater than 0.7 and a p-value of less than 0.05. The second step is to verify whether you have a high degree of correlation. Ideally speaking, you need to have a lot of green color cells or a lot of red color cells, but preferably green color cells. Then you can look at the total variance explained. Watch out for an eigenvalue bigger than 1. Ignore those components which have an eigenvalue smaller than 1. Step number 4 would be to look at the elbow graph or the Scree plot. Watch out for the elbow point. That is where you need to stop, and you can count the number of dots above the elbow point, which will give you the ideal number of components. Next step is to interpret the components. You can pay attention to rotated component metrics. Step 5 would be to summarize the interpretation. The next step would be to create a visualization of the percentage of the variance explained by each and every component. Step number 8, this is only optional, is to generate a path diagram. You can use either Amos for it, or you can go ahead and use StatCraft, which will create a path diagram. Step 9 is again optional. This is just to verify whether there is any relationship. If you have used orthogonal rotation, you will not see any relationship. On the other hand, if you have used any of the non-orthogonal rotation techniques, you may see somewhat of correlation between the components. The last step is to generate the factor scores, which can be used for further analysis. In this video, we have covered a lot of steps. I hope you have liked this video. I thank you very much for watching this particular video. I request you to subscribe to my channel, also like and share my videos. Thank you very much once again. Have a great day ahead.